Welcome! In this video I'll show you how to solve the Bessel equation. And this is an incredibly important equation since it will appear constantly in several areas of mathematics and physics, and it is very important that you understand how you can solve it. Solving it, of course, does depend on the value of this constant nu. So what I will do in this video is show you how to solve it up to the point where we need to put in the value of nu, and then I will make a few different videos for each case. Okay, so this sort of equation requires solution by what is called the Frobenius method. Now, the Frobenius method is very similar to the power series method. It has its limitations, maybe we can discuss it in another video, but basically what we will do is we will look for a solution of the form y is equal to the sum n equals 0 to infinity, some constant an times x to the n, but now we add x to the power s. And of course, s is some constant that we will need to determine later. So this we can write just putting the x to the s into the sum as an x to the n plus s. So this is the Frobenius method. Instead of just plugging in this, which is what we usually do in the power series method, now we include this plus s. So let's find the derivatives. So y prime, well, we simply derive each individual term. So n plus s comes down. So we get summation n equals 0 to infinity of n plus s an x to the n plus s minus 1. And the second derivative, now we get the exponent comes down once again. So we get n plus s and then n plus s minus 1 an x n plus s minus 2. Okay, so now we have everything we need. So let's just plug everything into the Bessel equation. So we get x squared times this thing right there. So let me copy it. So copy and let's paste it and bring it there. And then we get plus x and then times the first derivative, which is this. So copy paste. There we go. And then we have plus x. Actually, let me write this out. So x squared times y, which is n equals 0 to infinity of an x n plus s, and then we get minus nu squared summation from 0 to infinity of an x n plus s, and that is equal to 0. Okay, now let's simplify this a little bit. So notice that since we have x squared here, this sum doesn't depend on x, so we can simply multiply through, and instead of having n plus s minus 2, we get n plus s. So I'm going to copy this and modify it accordingly. There we go. So this x squared eliminates this minus 2. This x eliminates the minus 1. This x squared now adds 2. And yeah, and there's nothing new. Okay, now notice that these two sums have the same constants here, and they also have n plus s. So let's group them up together. So we get sum from n equals 0 to infinity, and then we have n plus s, and then we can factor it out. So we get factor of n plus s minus 1, right, from here. But then we have another one. This is n plus s times 1, so we get plus 1. Right, simply factoring out. If this doesn't make much sense, you can just multiply through and just do it manually, right? You multiply this, you add this, and then you will see that this is also possible. These two, of course, cancel out, and we get n plus s squared. So n plus s squared. And this, of course, multiplied by an x to the n plus s. So we already considered these two. Now, we also have this constant right here, actually, so maybe let's include it, because it also depends, or it's also multiplied by an x n plus s. So we can say minus nu squared, and now this times an x n plus s. We only have this term, right? Oh, that included the 0 when I made the circle. Of course, the 0 is not included. Only this sum is different. So we have sum from n equals 0 to infinity, an x n plus s plus 2. Now, here we must use a rule that is very important. It's not really a rule, it's kind of a trick. And we're going to say, let's define a new n, right, a new constant, which will be n plus 2. So here, instead of having n plus 2, we get n prime. And simply n, right, n thus is n prime minus 2. So our point, our beginning point here, when n equals 0, n prime is equal to 2. So this sum begins from the second part now, and you can then verify that it is indeed the same. I'll show you in a moment. And an, right, n is n prime minus 2, so this is n prime minus 2. Okay, and notice that this is, of course, the same as before, right? We haven't really changed anything. We simply changed the name of the variable. And how do we know? So before we had an x to the n plus s plus 2, and our sum started off from point 0. So our first term was a0, x to the, and then we get s plus 2. And now, if we do the same, we start with n prime equal 2. So we get a sub 2 minus 2, which is 0, x to the power 2 plus s, and there we go. It is indeed the same term. And you can check for any other terms if you wish. Okay, and finally, since n is simply a dummy variable, right? The name doesn't matter. It doesn't matter if you call it n prime, star, hello, how, it doesn't matter. You can say anything you want. So we can now change the name of the variable, right? We say, all right, n prime is equal to n. Let's just change it again, because it doesn't matter. As long as we hold the rules, the name itself doesn't matter. Okay, I'm gonna have to rewrite it there. So n and n and n. There we go. And I'm just going to make this look a bit better. So a n minus 2 x n plus s. Now let's begin writing out a few terms so that we understand what's going on. So let's begin looking at n equals 0. So of course at n equals 0, this hasn't really started yet. This begins at n equals 2. So at n equals 0, we have these terms. So we get 0 plus s squared. So we get s squared minus nu squared a0 times x to the s. But of course, s cannot be 0, right? So we don't worry about it. We are only interested in this part. We need this thing here to be 0. Either a0 is 0 or this thing is 0. So that means that if we want a0 not to be 0, then we need that s squared has to be the same as nu squared. So here we found our condition for the power s, right? The power that we introduced in this Frobenius method. So s has to be, let's write it like that, s has to be plus or minus nu. And nu is, of course, the constant, just as a reminder. Nu is the constant in this equation, okay? So there we go. That comes from the first term. This is often called the indicial equation, right? The indicial equation. Which is the equation for n equals 0. Now, so this is n equals 0. Now let's continue with n equal 1. So here we get s plus 1 squared minus, and now we know that s and nu are the same. So we can write this in terms of either s or nu. I will just choose to call s nu, but of course it doesn't really make much of a difference. Minus nu squared, and then this is multiplied by a1. This is equal to 0. Okay, and let's see. So here we get another condition. So here we get nu squared plus 2 nu plus 1 minus nu squared times a1 has to be equal to 0. So either a1 is 0 or this thing here is 0. These two cancel out. So that condition is the same as saying that nu has to be equal to minus 1/2. So unless nu is exactly minus 1/2, then we need a1 to be equal to 0. Right? So only the very special case, nu is equal to minus 1/2. This is not really necessary, but we will take a1 equal to 0 because otherwise we restrict ourselves in terms of the solutions. Now let's go for n equals 2. Right? We have to do as many of these as we need to understand what's going on with this problem. So n equals 2, once again, plugging it in, is s plus 2 squared, or actually rather than s, let's continue to call it nu. Nu squared plus 2 squared minus nu squared times a2. But now notice that we are at n equals 2, which means that this part now begins to function. So now we have plus, and then we have a0. Right? Because this part right here is n minus 2, so we get n equals 0. We are, of course, not writing the xn plus s because you can factor it out and that part can't be 0. So that is the reason. Now let's multiply it through. So we get nu squared plus 4 nu plus 4 minus nu squared. All of this times a2. This is equal to minus a0. So the nu squares cancel out. And here we get that a2 this is equal to minus a0. And here we have 4 nu plus 4. So let's write it 4 nu plus 1. Okay. Now let's continue. So here it depends how fast you are. I'm not really seeing much of a pattern yet, so I'm going to continue to write down terms until I can realize what is going on. So n equals 3. Now we get nu squared plus 3 squared minus nu squared times a3 plus a1 equals 0. Okay, so a3, this is going to be a1 minus a1 divided by, this is now of course the nu squares cancel out, so we get 6 nu plus 9. But notice here that this depends on a1, and we already found the condition that a1 had to be 0. So a3 is also 0, and thus a5 will be 0 and a7 will be 0. So n is 0 for basically for all odd n's, if n odd. Okay, so that is important to note. So let's go for n equals 4. So n equals 4. Here we get nu plus 4 squared minus nu squared a4 plus a2 equals 0. So again, the nu squares will cancel out. So we get a4, this is equal to minus a2 divided by, I'm going a bit faster, and here we get 8 nu plus 16. So 8 nu plus 16, which we can write as, so 8 nu, that is 8 times nu plus 2. And this is times a2, but we already found a2. a2 is this thing right here. So we get minus 1, which will be squared, divided by, and let's begin with this part. So we get 8 nu plus 2. We have a0, and then 1 over this part, which is 4 nu plus 1. Now, I don't know about you, but the pattern is not really that obvious to me. So I will continue. N equals 6. So here we get nu plus 6 squared minus nu squared. A6 is plus A4. This is equal to 0. So A6 is equal to minus A4 divided by, again, nu squares cancel out. So we get 12 nu plus 36. So let's factor out 12. So we get 12 nu plus 3. And let's see, then we have, let's plug in A4, which we already found here. So we get minus 1 cubed times A0 divided by 12 times nu plus 3 times 8 times nu plus 2 times 4 times nu plus 1. So slowly a pattern is emerging, and I already suspect where this is going. However, if you are really, let's just do one more, just to be super sure. We could already find the answer, but just to be sure, let's go for n equals 8. So here we get nu plus 8 squared minus nu squared. A8 plus A6 is equal to 0. Again, nu squares cancel out, so we get A8 is equal to minus A6 divided by, and here we have 16 nu, we can factor out 16, plus, and here we have 64, which is 4, right? 4 times 16. So I went a bit faster here. Now let's plug in A6, which we have right there. So when we plug it in, we get minus 1 to the 4th power A0 divided by, now it's very important that whenever you have this minus 1 cubed, that you write it as minus 1 cubed. Don't just write minus 1, or if it's squared or something like that, don't just say 1, because it's a pattern that you must see. So even though you could just write this as 1, don't do it. Okay, so then we have 16 nu plus 4. I don't know why I changed colors. So 16 nu plus 4, 12 nu plus 3 times 8 nu plus 2 times 4 nu plus 1. Now let's take a look at this. So we have a lot of powers of 4 in the denominator. So perhaps let's factor out some of it. So the numerator will be the same, minus 1 to the 4th power A0. But now let's factor out 4, right? All of them are multiples of 4. But notice that we have 4 times, right? We have 4 times 4 times 4 times 4. So we can't just factor out 4, we need to factor out 4 to the 4th power, right? Because this is 4 times 4, 4 times 3, 4 times 2, 4 times 1. So we get 1 from here, 1 from here, 1 from here, and 1 from here. So we get 4 to the 4th power. And then we have 4 times 3 times 2 times 1, which is 4 factorial. And what else do we have? Then we have nu plus 4, nu plus 3, nu plus 2, nu plus 1, just barely fitting in. So now it's looking a lot more, I think it's much more viewable, it's much more seeable, right? We can see now what the pattern is. And just to make it a bit more clear, let's write 4 here. We can maybe write it as 2. And this is not to the 4th power now, but to the 8th, right? Because 4 is 2 squared, so this is 2 to the 8th power. So now notice, how could we write in general the kth term? So we want to go, what is the kth term? So let's begin with this, and then we will check if we did it correctly by plugging in the other terms. So A8, now this is k over 2, right? Because we have 8, and that is a 4, which is k over 2. And if you go to the k equals 6, for example, this is 3, which is also k over 2. And if you go to the 4th case, k equals 4, we have 2, which is 4 divided by 2. So that seems to make sense. So it seems to be that we have minus 1 to the k over 2 power. Now a0 remains the same, there's nothing new there. Then we have 2 to the kth power, right? And then we have 4 factorial. 4 is k over 2. So in this particular case, we still have to check that it holds. And this thing right here is nu plus 1 times nu plus 2 times etc. until we get to n plus k over 2. If k is 2, for example, then of course k over 2 is 1, so we immediately stop here, right? So this is basically a product, right? It's basically the product. I'm going to write it like this, but if you prefer to write it as a product, I don't know, from k equal, or for, no, you can't use k because that's the upper limit. So from I equals 0 to k of nu plus I, then you can do that, right? Or I over 2, something like that. But I think it's a bit more clear like this, and it will also be useful in the future. So that's why I keep it like this. But if it's more comfortable to you, you can change the notation, of course. Now let's make sure that this is correct. So let's go to the other cases. Let's go to A6, this. So let's see, 2 to the kth power. K in this case is 6. So if we do it like this, we would have to have, let's see, factoring this out. Actually, let's factor it out just as we did to make sure that it's correct. So minus 1 cubed, a0, and we have 4 times 4 times 4, which is 4 cubed, or 2 to the 6th power. So that makes sense, that is 2 to the k. Then we have 3 times 2 times 1, which is 3 factorial, which is k over 2 factorial. And then we have nu plus 1, nu plus 2, nu plus 3. So nu plus 1, nu plus 2, nu plus 3, which is also, it goes all the way up to k over 2. So that makes sense, that's good. So it seems that our formula here is correct. However, it is a bit annoying because this doesn't really hold for all numbers, right? Because it does hold, but we don't have the odd numbers, right? So k equals 0, for example, they are always 0. So this is not really true for the odd numbers. This is true for the even numbers. So for that reason, let's now go from k to 2n. And that way, n will go 1, 2, 3, 4, 5, 6, blah, blah, blah. But since 2n is even, this formula will always hold. So that will make notation much, much better for us. And this is a very important step. So basically, instead of writing k, which could be even or odd, we go towards 2n, which is always even. So a of 2n will now be minus 1 to the k, which is now 2n over 2. So that is, of course, simply n. So minus 1 to the nth power, a0, divided by 2 to the k, but k is now 2n. Then we have k over 2 factorial, so we get n factorial. And then we have nu plus 1, nu plus 2, etc., until we get to nu plus n. Okay, and these are our coefficients. We don't know what a0 is just yet. Now, some books will just go ahead and tell you that a0 is, by convention, 1 over 2 to the nu power times gamma function of, I think it's nu plus 1. And I personally don't like to just tell you this right away. I would rather do this when it makes more sense, right? So I will give you a good intuitive idea, right? This is what a0 will be. We will choose that eventually, but I will not do it right away because I want you guys to get an idea of why that is. So here, notice that we have this messy notation, right? We have this just product of a lot of things. We can't even write it out explicitly. And we will use the gamma function to try to do this a bit better. So just as a reminder, if we have the gamma function of some m, this is the same as m minus 1 factorial. Okay, so that is very, very important. So here, notice that we kind of have a factorial, right? Because we have nu plus n times nu plus n minus 1, nu plus n minus 2, etc., until we get to n plus 1. But the problem is that we don't get all the way to like 3 times 2 times 1, right? Which is the way that factorials are supposed to end. We are missing this entire bit here, right? We only get to the point nu plus 1. So what I like to do here is that I multiply and divide here by nu factorial, divided by nu factorial. Because that way, now we have all this thing times nu factorial, which is, when we multiply all of this, nu plus n factorial, right? Because this right here is nu plus 1 factorial, then we multiply with this, and we go one step further, so nu plus 2, nu plus 3, and all the way until the nth term. Of course, how many terms there are depends on n. But this is a compact way to write it. Okay. Now, however, there is an issue because nu can have a whole range of values, and it can be half integer. So for that reason, writing it as a factorial can be problematic. Because the factorials are supposed to be real whole numbers, right? So having just this 1/2 in there is tough. So for that reason, we want to use the gamma function, which is defined for a much more broad range of numbers than the factorial. So we will use this relation right here. So if we have m minus 1 factorial, we get gamma n m. So this is basically gamma of nu plus n plus 1, right? So this is the same as the factorial of nu plus n. So for that reason, we can now rewrite all of this as the gamma function. So that is the gamma function of nu plus n plus 1. And we still have, of course, this nu factorial. However, as I mentioned, nu could perfectly well not be an integer. So for that reason, having it as a factorial is problematic, right? So we will use, again, this thing right here and write it as a gamma function. So instead of having factorial of just nu, we get gamma of nu plus 1, right? Because this is the same as nu factorial. So here we have gamma of nu plus 1. So this is the reason why in this constant there appears a gamma of nu plus 1, because by doing that we cancel out this constant here. I'm not going to just do it just yet because we still haven't given an explanation for this to the nu. Okay? So I think I'm gonna show you that just in case that it appears in your textbook. So there's two ways to write this. One is the way that I think is more intuitive, which is the one that we have, which is this thing right here. It isn't, of course, it isn't ready just yet. We still need to find more, basically the justification for this. But that is the way. And now if we plug in this value for a0, we get minus 1 to the n. And then this gamma here goes away, the a0 goes away. And then we have 2 to the 2n plus nu, n factorial gamma of nu plus n plus 1. So these two forms are, of course, equivalent. All right, so let's write down our solutions. And since this is the Bessel equation, the solutions we will call the Bessel functions, and they depend on the value of nu. Now, depending on the value of nu, they will be of different orders, and they will be of different kinds also, depending on other conditions that we will see later. So this is the sum from n equals 0 to infinity of a n x to the n plus s. However, there's a few things to note. First of all, we know that s has to be nu. either plus or minus nu, right? But there will be a different solution, which will be, in the case, minus nu. Okay, which we will note in just a moment. Actually, I'm going to write it maybe further down here. So the case j plus nu, now just as a reminder, in case you forgot, why am I talking about plus or minus nu? It comes from the initial equation when we found, right, for the case a0, we found that s squared had to be equal to nu squared, so s is plus or minus nu. So there are two possible values. Now, both bring you to the same results, right? So let's begin with j nu. So here we also know that an, right, we don't have a result for an, we have a result for a2n. So we can simply relabel n to 2n. And now we can plug in our result. So let's begin with all of our constants that don't depend on n. So we can take out, first of all, x to the nu, right? That doesn't depend on n. Then we have a0 gamma of nu plus 1. And then we have sum of n equals 0 to infinity of minus 1 to the n, x to the 2n, divided by 2 to the 2n, n factorial gamma of nu plus n plus 1. Okay, and this is the same just in case that you use a0 is 1 over 2 nu gamma of nu plus 1. This is the same, right? The only thing that changes is this. So you get x to the nu divided by 2 to the nu. And that's it. And everything else is the same. So sum of the exact same thing. So that is the result for the solution of the first kind, right? When there is nu, we call it first kind. And for minus nu, we actually take this exact thing, but we change nu to minus nu. We don't have to go through the same procedure again. I mean, you can if you want to, but it's not necessary. So we get a0 gamma function of 1 minus nu, sum of minus 1 to the nth, x to the 2n, n equals 0 to infinity, 2 to the 2n, n factorial gamma of nu plus n plus 1. And there we go. This is the Bessel function of the second kind, which is sometimes called Neumann function. So there we go. Now, to go further, we need particular values of nu. So we are going to take a look at the case for nu equals 0, for nu integer, and for nu half integer. So hopefully this video was useful to you. If it was, please make sure to leave a like on the video, comment, and subscribe, and maybe share it with some of your peers if they may find it interesting. And if you really enjoyed, maybe consider checking out my Patreon. So I'll see you in the next video. Thank you very much for watching.